Okay, so when we're measuring how things move, we care about four different aspects of that motion. What can we measure about an object's motion? What could we determine, put numbers to? We could tell how far it goes. We call that our displacement, how far it went. I'm just going to throw them up here. It's going to make sense in a second. What else can I measure about an object's motion? Yeah, Howard.
Speed.
How fast it's going. So that's a V measurement. What else can I measure about it? Yeah, I can measure how long it was moving. And there's one more that we are going to work with. Acceleration, the last one. How fast it's going fast, or how fast is the fast changing. That's why we call it acceleration, because those sentences didn't make any sense. So these four measurements are what we're going to basically be working with, and we can work within them. So we have four kinematic formulas that involve this stuff, and we have to also have the one we already know. So the one I showed you yesterday is first on the list. So the one from lesson 3 is, there's four, so space them appropriately. There's four formulas here. So A is equal to the final velocity minus the initial velocity. Okay, let's continue with this part. Okay, so that's our first formula. That's the one we used in the previous lesson, lesson 3, and we only used that one. The next one is our average velocity formula, but with a little addition. So we're going to go distance is equal to final velocity plus initial velocity over 2, all multiplied by time. So this is our next formula. Now, I have written down here, if you've read ahead, we can derive these equations from graphs of motion. I will not be doing that as part of our lessons. Some of those are written in the old book that we had, but we can do it if we need to, but I think it's not worth it. The next one is my personal favorite. D is equal to, let me make that look nice. V naught multiplied by T plus half of A T squared. Let me slide this up a bit, just there. That's that one. And then the last one is the final velocity squared equals the initial velocity squared plus 2 times acceleration times displacement. So these are the four formulas that involve acceleration. And it's important to note that, while these are four different formulas, they are all also the same, because they all will describe the same motion. The object still did the same thing, but we can describe different pieces of it with whatever measurements we care about at the time. So the main difference between all of these is what it doesn't have in the formula. So of the letters at the top, which letter is absent from my first formula? Yeah, so there's no displacement measured. I'm going to write no displacement. So there's no displacement measurement in that first one. So in all of the questions yesterday, when you guys were solving all of them, none of them cared how far the object went. What's missing from my second formula? Yeah, the acceleration term. So, I'll keep writing this poorly. No acceleration vector. So I can describe an accelerated object without knowing the number for that acceleration. I can still describe how far it went, how long it was going, the two speeds involved, can describe an accelerated object without knowing the number of that acceleration. What's missing from my third one? It's a little trickier. Final velocity. So this is no final velocity. I know some of my printing in the back was a little bit weird. Velocity is a lowercase v, as badly as I print it. Sometimes it is lowercase, so if you're being careful with that. Capital V is for voltage, that we'll get to much later. but lowercase v is bad as I like to print it. So no final velocity, so we don't care what the speed is at the end. We can still do all the other parts of the formula. What am I missing at the end? You've almost figured it out for sure by now. Time. We're no time measurement, so we have no counting of the intervals, but we can still do the speeds, the accelerations, and the distance. So depending on what measurements were taken, or in our case, what the word problem has written in it, we choose a different formula that fits our needs. And don't forget, we still have this formula at the top. V is equal to displacement over time for constant velocity. Because more appropriately, it's our average velocity. So average velocity is equal to displacement over time as opposed to any change in that velocity. So we don't care about the beginning and the end. It would just take the average and that works. It's worth pointing out here that this formula is basically a rearrangement of that formula. Because like this is just average. Add them together and divide by 2. That's just average velocity in here. So it's basically the same. Let's do the graph. So we're going to do this lovely graphing example here, where given the velocity time graph that we have here, find the acceleration and the displacement. So all of the important things are written right on here. I even went ahead and put the numbers on for you, so you can find out all of these things. And it has a title, which I didn't put on here. It's velocity versus time. Very creative, right? So I got to figure out a few different things about this thing. The first one is acceleration. How will I find acceleration on this graph? What do I measure acceleration in? What's the units for acceleration? Do you guys remember that from lesson 3, the last one? Yeah, so acceleration is always measured in like meters per second squared, right? And so how can I get meters per second squared out of the graph? Okay, so I know it's probably a little bit of a stretch, but I'm going to explain it because I don't need you guys to be able to tell it back to me. If I have meters per second and seconds, I want the slope. So I want the slope of this line is going to give me the acceleration of this object. So the slope of the line is your velocity over time. So we can do our slope calculations. We can go from this point to this point, do our y2 minus y1, x2 minus x1 for our slope. So what is my top y value on the graph? 9, thank you. 9. Oops, I don't need this in pink. Let's go back to the blue color. Back to the blue color. It's 9. And what's the lower y value? 3. Right, I'm doing second y, first y. So it's this line, this line. The time is easier. It's less exciting. It's 10 and 0. I know, this one was easy. So it's like this line and that line. So that one was easy. So for our calculations, very, very challenging. We get 6 over 10. Very exciting. And so we would get 0.6 meters per second squared as an acceleration. And so this gives me my meters per second kind of vibe here. So this is our graphical analysis for this lovely thing. Now it's part of the difference that I didn't do in a previous lesson, but I'm going to basically show you guys the aspect of it here. So we've already found the slope of this line. The next thing what we're going to do is we're going to find the area under this graph. So we want to find basically all the space down here. What is all of this space going to work out? So what shape is this shape? For our triangle. So we add the rectangle and triangle together. Now remember, when we're doing this, it is the triangle, just the pink part. So the base is 10. What's the height of my triangle? 6, right? It's not 9. It's from 3 up to 9. It's 6. The pink part is 6. Which is easy. 30. So, total area 60. Now, 60 what? What have I found? What is the 60? We know the number 60. That one part is easy. What am I measuring? How did I find these two things? Okay, what is the 10 measured in? Seconds, right? So I have this, I'm just going to go down below as like an aside. So seconds multiplied by, what is the 3 measured in? It's measured in meters per second. What is seconds times meters per second? I know I'm sliding right down there, so. That equals meters. So what I've actually found here is 60 meters. So what is this measurement that I've found? What part of the object's motion have we determined? How far it went. So it's displacement in this case. So area equals displacement. So that's the important part of what we've discovered. So the area under specifically a velocity time graph is this displacement. So that's what we have found. When we first read these word problem questions, the strategy is to write down all the different numbers beside to figure out what each one is, so we figure out what we're looking for and what do we have in what units. So I just go across it till I see a number. An object is initially traveling at a velocity of 7.00. Great. What have I measured here? If I'm looking at this lovely thing, which symbol should I give this number 7? Yeah, this is my initial velocity for V naught. So the first one gets to be V naught is 7.00 meters per second. That's what I'm going to write down. I keep reading along the question. It accelerates uniformly over a distance of 18.3 meters, which means I know this is a distance of 18.3 meters. And the next one, really obviously in this case, in a time of 1.75 seconds. Calculate the acceleration of this object. Great, so I wrote this really easy because it's not going to be too confusing in its wording. These are the things I need to figure out. So that's the first step, is just get everything I do know in a nice, easy to read spot. And this also allows me to do my second check, is are all these units going to agree? Do I need to do any conversions before I start? No, these are all good. Everything's matching. Meters, meters per second, seconds. All of it's good. There's no kilometers. There's no minutes. There's nothing I need to convert. So I now need to go probably flip over your page or break out your formula sheet, whichever one's closer, and choose which of the 4 formulas I showed you have these letters and no others. So they need those 4 letters and no other letters. We're going to use the third formula, which is the displacement equals V naught T plus half of A T squared. Fantastic. So the good news, that's our formula. The bad news is I want to find This is my unknown. So what I'm going to do, I have two examples here, and I'm going to do them two different ways. For the first one, I'm going to take this formula, throw all the numbers into it, and then solve. For the second example as a preview, I'm going to rearrange all the letters first, then input the numbers. Both of these methods are perfectly valid. I just want to show you both of them, and it's personal preference or context of the question to decide which one is better at the time. They're both fine, but sometimes one is easier than the other. So in this case, I'm just going to take every single number from here that I know and slot it right in, and then do the algebra second. So I know the displacement. It's, turn it back on, 18.3 equals my starting time, 7.00. Time is 1.75. Adding to, I'm going to change it right now to 0.5 because that's going to be easier to type into my calculator instead of the 1 over 2. And then I'm going to put an A here. And then I'm going to put a 1.75 squared term there. So that's all of the numbers that I know. And so in this case, I'm going to type each of these into my calculator and simplify a few of them. Specifically, I'm going to put these two together first, and then I'm going to put everything that isn't A over here together next. Now, I haven't done this, so I got to get my calculator out and do this. So the first one, 18.3 isn't going to change, so it's going to stay right here. But then I'm going to multiply these two numbers together. 7 times 1.75, 1225. As an aside, while you guys are doing this, I know I write 7.00 on the page to show 3 significant digits. Don't write 7.00 in your calculator. That's just 3 extra buttons you didn't need to push. And then we'll do plus 0.5 times 1.75 squared. Make sure your calculator is doing the squared button first before you do the multiply by a half, because that's the proper order of operations. You got to do the exponent parts before the multiply parts. So make sure your calculator is doing that. I get 1.53. That's enough. I'm going to keep those. That's enough decimals. A at that case. So what I have now is just a linear equation that I need to solve. So I need to get all the numbers away from this A. I need to get this number over there and this number over there. Which one should I do first, the 12 or the 1.53? Which one goes first in my algebra? The 12 one first. I got to do the add subtract steps before the multiply and divide steps. So first step here is subtract 12.25 from both sides. I'm showing all my steps. Most people just do this in their calculators. 18.3 minus 12.25. I get a number 6.05 equals 1.53a. Now I can just do my division step. Division step 1.53 over 1.53. And now all that's left is the A term. Get the calculator out. 6.05 over 1.53. 3.9542 is already too many numbers. And that's all the calculator is going to do for me now. So now that we have all of those decimals, we need to now, we have our answer in number form. We need to do now our answer in like response form. So how many significant digits should I keep? 3, right? Everyone should keep 3. So we got to round it to 3. So A will equal 3.9. That's terrible. Let's clean that up. 95. We write our units. Acceleration is meters per second squared. And do we have a direction given in our question? We do. It's right here. So in this case, this direction is to the right. And that's in the question. So that's where we go. So that's our final answer here. 3.95 meters per second squared to the right. And that's our complete final rounded units, direction, answer, all together. Next question, similar, but of course different. An object accelerates to the right uniformly from rest in a time of 2.7 seconds. In this time, it has traveled 20 meters. What is the final velocity? So we're going to write down each of the pieces in the question to start with. So uniformly from rest, a very important one. The from rest sentence tells me my initial velocity is 0. So we're going to start by writing my initial velocity is equal to 0 meters per second. Very nice. The next sentence is my times part in the sentence, which is 2.70 seconds. I know my displacement will be 20.0 meters, and I know final velocity is what I am looking for. So those are the 4 letters I have. Until you guys are super comfortable with your formula sheets, you'll probably have to keep checking each time to decide which is the right formula. And until you basically have your formula sheets reasonably memorized, you're going to want to do this listing step first, because then you'll get the right formula every time. Which numbered formula do I want? Which of those 4 formulas will give me what I need? It's number 2. Number 2, the second formula that I gave is the one that I'm going to use. So that written out looks like this. D is equal to VF plus V naught over 2 multiplied by T. So that's the formula right off the page. It's the same on your formula sheet, written just like this. What am I going to do first? I'm going to rearrange this one entirely in letters before the numbers go in, just as a side example to the other one. What shall I do first? I got to get rid of that T first. So we're going to divide both sides by T, divide by T, and so my left side will look like this, and this side will look like this. What's the next math step that I have to do now? I got to deal with what? I got to deal with the 2 next. So we're going to multiply both sides by 2, multiply by 2. So my left side now looks like 2d over t, and the left side looks like vf plus v naught. I now only have one thing left to do, and that's remove the V naught step, minus V naught, subtract V naught. I'm just going to put it there because it looks silly, sliding down so you guys can see. I now have my final formula. The final velocity is equal to 2d over t minus V naught. And that's now the formula fully rearranged. At this point, I'm going to put the numbers in now, which is pretty convenient because I know this number is a 0. It's very handy. I don't even have to worry about it anymore. It's a 0. So I just get to write 2 times the displacement divided by the time. So that's the only calculator button I have to actually push. So for calculators, this is actually the easier way to do it with all the letters, because I could just do all that with my algebra skills, and I only need to break out the calculator for the very last steps. I don't have to do multiple calculator steps. So this one's actually not that bad. It's 40 over 2.7. Nice. I get 14.8148, bunch of numbers. And now I can finish up my question as VF equals, and I can start doing all of my rounding thoughts. How many significant digits should I keep in this question? I'm going to keep 3. So it's going to be 14.8. And then it's a final velocity, meters per second. It has a direction to the right in this case. And that's all the information I need. I have final velocity, right number of significant digits, I have the correct units, and it's a vector, so I need a direction. So that's all of the things that we need for this question.